Today we're going to take a look at a special type of series we call a power series. All right, so just to kind of reflect back on what we've seen already, we know that we can approximate a function with a Taylor polynomial. Now, a Taylor polynomial goes out to some number of terms and then stops. So it's finite. So, for example, e to the power of x, we've seen this before, is 1 plus x squared over 2 factorial plus x cubed over 3 factorial, and that would be the third degree Taylor polynomial. And we could extend this out and we could make a fourth degree or a fifth degree Taylor polynomial for e to the x, but a Taylor polynomial always has finite terms. Now, the more terms we add, the better the approximation gets. And if we really wanted to make this better and better and better, we would just keep on adding more terms and we would have infinitely many terms. Well, if we have an infinite series to approximate a function, we call it a power series. So it's really the same sort of idea as these Taylor and Maclaurin polynomials, but rather than being a polynomial, we call it a series because it goes on forever. So we would just extend this out more and more and more terms. We have the nth term out there. But you can see after the nth term, we have plus ... indicating that it keeps on going. And whereas a Taylor or Maclaurin polynomial is an approximation for the function, the power series converges exactly to the function. So these two behave exactly the same. All right, so to define a power series, it's really just a polynomial that extends forever. So we have the initial term, a sub 0, then we have a sub 1 times x, a sub 2 times x squared, on and on and on. And we could center the power series at some number other than 0. We'll call that number c, and this would just have the effect of shifting it over c units. Okay, so the power series can be viewed as a function where the domain of that function is all of the x values where the power series converges. So we can plug in different values for x. We know that some series converge, some series diverge, and any value of x that we could plug into this series and have it converge would be part of the domain. Now, every series converges right at its center, so at the point where we make the series equal to the function, because if you plug in that value c for x, you add up just 0 plus 0 plus 0 plus 0, which converges. All right. There are three ways that a power series can converge. The series could converge only at its center. The series could converge over some finite radius, so there's some number r, where for any values less than r, the series will converge. Or the series could converge for all values of x. And if we go back to option 2 there, the value r we call the radius of convergence. So it describes the size of the interval of x values where the series converges. We'll take a look at a series that we're already familiar with, a geometric series. We know that a geometric series is formed by multiplying by the common ratio r. And we know that a geometric series converges to a over 1 minus r if the absolute value of r is less than 1, and diverges if the absolute value of r is greater than or equal to 1. So for any values of r between -1 and +1, we know the series converges to a over 1 minus r, otherwise it diverges. So now let's take a look at this, 1 plus x squared plus x cubed, on and on and on. That's a power series right there. But it turns out this is a geometric series because our common ratio is x. So we know this adds up to a over 1 minus r. The initial term is 1, the common ratio is x, and we know this converges for all values of x between -1 and +1. So for this power series, we would say that the radius of convergence is 1. And the interval of convergence is from -1 to +1. So for all values of x from -1 to +1, we know the series converges. And let's take a look at this graphically to make some sense of this. Let's graph the function 1 over 1 minus x. And now let's start graphing this power series. Now, it's not practical for us to graph the actual series because we can't graph infinitely many terms, but we can graph some of them and get an idea of how it's behaving. So if we start with that very first term, now we wouldn't expect this to be very good. That's equal only right there at x equals 0. If we graph the first two terms, there's our tangent line. If we graph the first three terms, that gets a little bit better. The first four terms is even better. And now let's go all the way out up to x to the power of 10. That looks really good over the interval from -1 to +1, because we wouldn't expect this series to approximate this function anywhere outside of that interval. So as we move to the left beyond -1, we don't expect our power series to conform to the function because that's outside of the interval of convergence. And as we add more and more and more terms, that little tiny gap right there, as we get close to -1, is going to close, and the power series would conform exactly to the function 1 over 1 minus x up until -1, and then it'll still diverge. All right, if we want to figure out what the radius of convergence is, we use the ratio test. So we want to find the radius of convergence of this power series. So let's use the ratio test. Increase n by 1. Simplify. We can cancel some things out here. That x can come to the outside because it doesn't depend on n. And the limit as n goes to infinity of n plus 1 is infinity. So no matter what x is, some number times infinity is going to be infinity. Well, this is greater than 1, which the ratio test tells us diverges. So the only point where this series converges is when x equals 0, right there at the point where it's centered. So the radius of convergence here is 0 because it converges only at a single point. Let's find the radius of convergence of this power series. So we apply the ratio test, simplify, cancel, and we end up with x minus 2. Well, we know that the ratio test tells us this converges if this limit is less than 1. So the radius of convergence is 1. All right, let's try another one. So we increase n by 1, and notice for x to the power of 2n plus 1, we replace n with n plus 1, so that's 2 times n plus 1, which as you simplify becomes 2n plus 3. Same thing goes with the 2n plus 1 factorial, that becomes 2n plus 3 factorial. The negatives go away because of the absolute value. We can simplify down our factorial and our exponent, cancel, and we can see here that since we have n squared on bottom and just x squared on top, and recall that x is just a number, so you have to set x as a number, n keeps getting bigger and bigger and bigger, that's always going to go to 0, which is always less than 1. So the interval of convergence here is infinity, because no matter what value of x we use, this is always going to converge. Okay, so we've seen the radius of convergence. That gives us an idea of the size of the interval. We also want to look at the interval of convergence, which is the actual values of x for which it converges. And the one thing that finding the interval of convergence doesn't tell us is whether or not the endpoints converge. So we find the interval of convergence, we identify the endpoints, and we have to check the endpoints individually to see if they do or do not converge. So we want to find the interval of convergence here. So first we apply the ratio test, simplify, and we find that this converges for absolute value of x less than 1. So the radius of convergence is 1. Now if we drop the absolute value there, we get x between -1 and +1. So we know that this series converges for values of x from -1 to +1, but we don't yet know if this actually converges at -1 or at 1. So we check those each individually. So we check x equals 1, replace x with 1. 1 to the power of n is just 1. This is the harmonic series which diverges. Replace x with -1. This is the alternating harmonic series which converges. So the interval of convergence goes from -1 to 1, including the -1. Find the interval of convergence here, so we apply ratio test, simplify it down. we know that this is less than 1. Well, notice there's that 2 in the denominator there. So if we multiply that over, now we can see that our radius of convergence here is 2. So this converges over a wider interval. Solve that inequality, and we can see that this converges for values of x from -3 to 1, but we don't yet know if this converges at either of those endpoints, so we check those. Okay, so check x equals 1. Well, if we let x equals 1, that gives us 1 plus 1 to the n, which is 2 to the n, and that cancels with the 2 to the n on bottom. So this is the sum of -1 to the n, which just alternates positive 1, negative 1, positive 1, negative 1. That diverges by the nth term test. Check x equals -3. So that gives us -2 to the power of n. Well, you can split that -2 to the n to -1 to the n times 2 to the n. So 2 to the n over 2 to the n cancels, and -1 to the n times -1 to the n is just 1, and this is the sum of 1, which again diverges by the nth term test, so neither of these endpoints are included. The interval of convergence goes from -3 to 1, not including either endpoint.